Assalamu alaikum. So here we are with the second lecture in our online lecture series, and today our topic of discussion will be mental models and representation. In our last lecture, I already explained you some design principles and heuristics, and while explaining them, I already told you that uh, in the latest edition of Don Norman, there is a seventh principle which is based on the mental models and the conceptual models. So today we'll be discussing solely on the mental models and representation. So let's start our lecture. So a mental model is the understanding you hold in your head about the world around you. So how you take into account the environment and how you assume that the system would work based on your understanding. That is the definition of the mental model. And basically it's an internal simulatable understanding of external reality. So simulating a mental model allows you to make predictions and figure out how to achieve your goals out in the real world. So a good interface will give the use a mental model of the system that it represents. In that way, we can help users learn how to use our interfaces as quickly as possible. Now, the next thing is the representations. So representations is the internal symbols for an external reality. So in order to develop good mental models, we need to give users good representations of the system with which they are interacting. So that's what we will talk about in this lecture, creating representations that help users develop accurate mental models of our system. We'll start by talking about mental models in general and how they apply to the interfaces with which we are familiar. Then we'll talk about how representations can make problem solving easier or harder. We'll see some examples. After that, we'll talk about how metaphors and analogies can be useful tools to create good representations that lead to accurate mental models. Then we'll discuss how user error can arise either from inaccuracies or mistakes in the user's mental model, or just from accidental slips despite an accurate mental model. Finally, we'll close by discussing learned helplessness, one of the repercussions of poor interface design, as well as expert blind spot, which is one of the reasons why poor design can occur. So let's start with defining the mental model in detail. So a mental model is a person's understanding of the way something in the real world works. So how something works in the real world, how you simulate it in your mind is the thing which is related to the mental models. It's an understanding of the processes, relationships, and connections in real systems. So using mental models, we generate expectations or predictions about the world, and then we check whether the actual outcome matches our mental model. Sorry for this noise of the mobile. So let's take an example of a basketball. Consider that you are holding a basketball, because generally we all probably have a model of what will happen if I try to bounce this ball. Of course, it will come back. So you didn't have to see it come up to know what would happen. So if you bounce it, it will come back to you, and even if you are not watching, it's okay, because you know that it will come back. So you use your mental model of the world to simulate this event, and then you use that mental simulation to make predictions. When reality doesn't match with our mental model, it makes us uncomfortable. So let's see an example. So if you try to just make a goal through this basketball, and you work with everything, every tactic, and still it doesn't work. So even if you simulate it in your mind, it is not guaranteed that it would work every time in the same manner as you have predicted it. And when it does not matches with the reality, if the mental simulation does not matches with the reality or the simulation with respect to our mental model, it makes us really uncomfortable. Even though if sometimes if I think that if I perform this activity and the result will be this, and if it's different than what I thought, then of course sometimes I get frustrated, sometimes I get disturbed, sometimes I get anxiety. And I think this is the a kind of normal for every person uh, when uh, when they do something and the outcome is not up to the expectations. So we want to know why our mental model was wrong. Maybe it makes us curious, but when it happens over and over, it can frustrate us. It can make us feel that we just don't know what we are doing. So designing systems that act the way the user expects them to act is the main goal of this uh, series of lecture, to uh, to design the system that could match the mental model. And of course, by doing so, designing systems that teach the user how they react. So if we can design a good system which can match our mental model, it will help us to teach the user as well that how to use that particular interface. So let me just change some things. Okay, now it's good. So mental model is quite related to the education, and I bet that if you just search out Google or if you Google mental models, you will probably find just as much about them in the context of education as in the context of human computer interaction. So mental model is not a uniquely HCI principle. And when you are designing an interface, you are actually playing very much the role of an educator, because you are teaching the users that how to use the interface, how to uh, like you are providing a guideline to the user that how to use the interface so that the system would work based on their mental models. And of course, good representations show the user exactly how the system actually works. And we will talk about representations shortly, which is an important phenomenon, by the way. But in order to provide the representations, we have to know that what the user is actually thinking, what is the conceptual model of that particular user. So that's actually a very useful analogy to keep in mind. Your goal is to teach your user how the system works through the design of your interface. But unlike a teacher, you don't generally have the benefit of being able to interact and explain things directly to your user. Most users don't watch tutorials or read documentation, or if they do, they don't want to. You have to design interfaces that teach users while they are using them. That's where representations come in. Representations is an enormous challenge, but it's also incredibly satisfying when you do it well. And we'll see some examples where you will understand this concept much better. But look at this picture. What it tells us is that the psychologist, if we take it in the context of education or in any other domain, they try to predict the cognitive model of the user, and it provides the explanation of the user's mental model. But the designer, they try to model, they try to understand the conceptual model from the user by knowing its user, and then they plan the design which kinds of provide an explanation to the user. So it's like uh, the designer tries to model a designer tries to develop a conceptual model of how the user will think the system will work, and then it's a kind of a trial and error method. So it's a kind of a continuous and gradual improvements in the interface design to match the conceptual model with the mental model of the user. So let's see the mental models in action. So let's talk a bit about mental models in the context of the climate control systems we see on automobiles. Let's consider this 1989 Volvo. Of course, it's an old car, so let's talk about how the climate control system would work back when these cars were introduced. So consider it's a very hot day outside, and these are the controls which were normally present at the time of this car, the introduction of this car, which is 1989. And by looking at these controls, how would you make the air temperature colder and the air come out faster? So naturally, as a car user, I'm not the user of the car which were introduced in 1989, but by looking at its design, the natural thought to me would be to turn the fan speed. Let me turn on my pointer. So my first thought would be to turn on the fan speed up over on the right, like this one, and the air temperature to the blue side over onto the left. So if I just like slide it to the left, blue, it's my assumption that the blue is like cooler air, and this is a kind of a fan, like fan notation. And if I just turn it to 2, 3 and 4, so it will be the intensity of the air which will flow through this particular action, which of course represents the fan speed. But this doesn't actually make the temperature any colder. It just disables the heat in the car. Now the dial on the top, basically this one. So the dial on the top right has to be turned on to make the air conditioning actually work. Now you have to turn it to this particular mark to allow to actually make the car cooler. So just sliding the latch on the blue side doesn't actually turn on the air conditioning. So to make it colder, you have to both slide the lever over to the left and turn this dial to the red area. Now of course it's not visible here, the color is not visible here, but this is the red area and you have to turn it on to this point. It's a kind of hard to see in this, but this little area over here on the left side of this dial is actually red. The red area on the air conditioning control designates the maximum coldness. Now first of all, my thought is like, what? The red means hot to me, and this red indicates that it will provide the maximum coldness. This also means that you can turn on both the heat and the air conditioning at the same time, and neither of them blowing out if your fan is turned off. So none of these really match my mental model of how this system works, and the colors used here do nothing to correct my mental model. There is a control here that if you turn it to blue, doesn't make the car any colder, and if you turn this other control to red, it does make the car colder. And my first reaction is, come again? So back in 1989, there was a lot of room for improvement on designing the climate control system for a car like this. Let's see if we actually did improve that by talking about a new car, that is Nissan Leaf 2015 model. Now this is the car which is like a new version, and I should relate to it because this car is of my generation. Now let's see the temperature control here in this case. Now in this case, You can see here the push button, which is here, and this one, and this is the AC button, and this is a kind of a button with which controls the air inside your car. Now if I push this button and if I push this one, or like if I just uh, turn this to the blue side, then my car gets cooler. I understand this and I can relate to this because most of the current cars have the same system as this one. But the problem is, if I want to make it like if I want to make the control uh, like automatically, if I want the car to control the air conditioning automatically, I can push here this auto button and it will control the car. But if I want to push it again, it will not turn off until and unless I turn off this button, which is the uh, controlling the flow of air inside the car. Now I do not understand this point, and it does not fit my mental model that how would why is such a thing, mm, why this is such a system which I cannot turn off until and unless I turn this thing, the flow of the air control inside the car, off. So of course, somewhat or some things in this system match my mental model because it refers to most of the systems in the car, but some things still needs improvement. And with respect to the mental models which we simulate in our mind before like interacting with the system at all. Now, mental models can be used for learnable interfaces. Matching our interface design to user's mental model is a valuable way to create interfaces that are easily learnable by users. So, there are 5 principles to leverage for creating learnable interfaces. These principles of learnability were proposed by Dix, Finlay, Abbott, and Wheel in their book Human-Computer Interaction. So the first one here is predictability. Now what it says is, look at an action. Can the user predict what will happen? For example, graying out a button is a good way to help the user predict that clicking that button will do nothing. So we can predict easily by seeing that gray color that it has been disabled. And if we like click on it, if we press it, it will do nothing at all. The next is synthesizability. So not only should the user be able to predict the effects of an action before they perform it, they should also be able to see sequence of actions that led to their current state. Of course, that can be difficult in graphical user interfaces, but something like the log of actions that they can see in the undo menu can make it easier. Command line interfaces are actually really good at this. They give a log of commands that have been given in order. Now, if you are familiar with MATLAB or if you are familiar with any other language like Python, it provides you the command history where you can see that what commands have you run and how you have reached to the result which you have obtained through running all those commands. So that refers to the synthesizability trait. Now the third is familiarity. This is similar to Norman's principle of affordances. The interface should leverage actions with which the user is already familiar from real-world experiences. For example, if you are trying to indicate something is either good or bad, you will likely want to use red and green instead of blue and yellow. And as I previously said in my slide, that the it was very awkward if I have to turn the dial to red, because as per my understanding or as per my mental model, red represents hot, or red represents stop, or red represents any danger. So that's how my mental model simulates this representation of the red color. Now, if somebody uses the red color, it comes to my mind naturally that I should stop, or it is bad to proceed with this color. And with the green, it is a kind of a norm that okay, it's good to go, we are good to go with this color. Similarly, if you see the traffic lights, red is for stop and green is for going. So these color norms actually play a decent role in maintaining the affordances. And if I use blue and yellow instead of red and green, I have to reconsider my mental models for such color coding, and that's not good at all. You have to be you have to leverage the user's understanding first, rather than changing the norms with respect to your choices. Now the fourth is generalizability. Now, similar to familiarity in the Norman's principle of consistency, knowledge of one user interface should generalize to others. If your interface tasks that are similar to other interfaces tasks like saving, copying and pasting, it should perform those tasks in the same way. So it's like the Norman's principles of consistency, that it should follow the same norms which have been available in the interfaces which are similar to the ones which you have designed. Now the last one is consistency. Consistency is slightly different than Norman's principle of consistency. This means its similar tasks or operations within a single interface should behave the same way. For example, you wouldn't want to have Ctrl X cut some text if texts are selected, but close the application if there is no text selected. The behavior of that action should be consistent across the interface. So it's like if you press Ctrl X if your text is not selected and your window gets closed. So that is inconsistency within the interface itself, and it should not be there, because it would affect the mental model, because the users didn't uh, simulated that kind of egg by when they tried to press Ctrl X. Now, using these principles can help the user leverage their existing mental models of other design, as well as develop a mental model of your interface as quickly as possible. I think I should stop here because it would be better if I would make only the videos for 20 to 25 minutes. It would be easier for you to rewatch it. It would increase the rewatchability rate as well. So I would stop here, and then we'll talk about something more in our next video lecture in the same series. Thank you.